Okay, let's start with this week's tutorial. This week's tutorial is basically of 3 questions, and it is fairly simple ones. Yeah? So I hope all of you have submitted your tutorial solutions in the provided Dropbox in your on your model shelves, right? So if you haven't, then do so, right? Before maybe, I'm not sure, but at least a few minutes late submission will not be penalized, right? Okay, so please try to submit your solutions just in case. I don't want anyone to miss out on this 10% that has been allocated for your tutorial submissions, right? And please do remind your friends as well, right? So let's start off with this week's tutorial. So there's 3 questions. So tutorial question number 1, right? Question number 1 states, for the following circuit, if the input voltage is equal to 1.5, what is the voltage output, right? So this is the circuit that has been given to you, right? So you can see that there is 2 inverting amplifiers in series, isn't it? So you can see whatever voltage you have been supplied is first amplified, right, at this particular point over here. And then whatever voltage you have at this particular point, right, at VO1 is again amplified. Thus, we have 2 inverting amplifiers in series, isn't it? So our job is first try to find our V out at this particular point, right? So our V out at this particular point will be basically the total resistance over here, right? That forms my R1 and the total resistance over here, right? So it is basically R1 divided by R2, right? Either way, whatever way you want to label it, but the total resistance over here divided by this total resistance will give me the gain of this inverting amplifier, right? So far, I mean, like by now, all of you must be aware with inverting and non-inverting amplifiers, right? So we are supplying 1.5 volt, right? So the gain of this particular inverting amplifier will be 30 kilo ohms, right? 20 plus 10, 30 kilo ohms divided by 10 kilo ohms, right? And since it's an inverting amplifier, it will be negative 30 divided by 10. So that is basically equivalent to -3, right? So the gain of this amplifier is basically -3, right? Multiplied by our input voltage, that is 1.5, right? So I'm going to get an output voltage at this particular point, which has been inverted and amplified. So that will be equivalent to minus 4.5 volt, right? So if you are to write it into simple equation, so voltage output is equal to voltage the gain, right? That is minus 30 upon 10 times the input voltage, that is 1.5. So my gain is, I mean, my total output voltage is minus 4.5 volt, right? At this particular node, right? And then this same voltage is now acting as an input to this particular inverter circuit over here, right? So what we do is take this voltage, right? This now becomes my voltage, input voltage, right? To this particular amplifier over here. So the gain of this particular amplifier is minus 10 kilo ohms upon minus 10 kilo ohms, right? So that is basically equivalent to 1, right? So the gain of this will be 1 times my input voltage, that is now minus 4.5 volt, isn't it? The voltage at this particular node. So minus 4.5 multiplied by minus 10 upon 10, right? So that is going to give me an output voltage of 4.5 volt. Okay. So all of you should have got your V out as equivalent to 4.5 volt, right? This is the answer. Question number 2, right? Question number 2. Okay, just before I move on to question number 2, anyone has any queries regarding question number 1? Okay. Question number 2, for the following circuit, if all resistors are of value 20 kilo ohm, and if V1 is equal to 3.2 volt and V2 is equal to 1.8 volt, what is your output voltage? Okay. So just considering this particular circuit that we are given, right? You can see, right? These two particular branches, right? These two particular branches are in parallel, right? So what happens is that, like, you know, in an inverting amplifier, this particular node at this particular point, there is a virtual ground, isn't it? So these two nodes are connected. So whatever voltage we have at this particular node is the same voltage at this particular node as well. So this is also virtually grounded. So if you see closely, you can see, right? You can see that this particular branch over here forms one set of inverting amplifier, okay? While this resistor with this R3 forms another set of inverting amplifier, okay? Or the other way you can see is, right, let me erase this. The other way you can see this is that the current, right, the current in this particular branch, right, the current in this particular branch is my I1, right? The current in this particular branch is my I2. Now, what you know is that this particular node over here has an input volt, is virtually grounded, right? Isn't it? Right? So basically this part is virtually grounded, right? So what happens to the total current? Whatever current you have at this particular branch, and this in this particular branch, what happens is that it does not go to the op amp, rather it flows into this R3 branch, okay? Right? You can read this as there's no current being flow. I mean, there's no current going to be flowing into the op amp, but rather all the current that you have goes over here, right? That is your I3 total, okay? Please excuse my drawing at the moment, right? I'm using the mouse to draw, so that is why this is happening, right? So you can see that whatever current you have in this particular branch, right? Whatever current you have in this particular branch adds up with this, whatever current you have in this particular branch to give you output at this particular branch, right? So all you need to know is that you can perform your nodal analysis in this particular case as well. But the simplest method is to consider this: the V2 is being applied to a one set of inverting amplifier, while V1 is again being applied to another set of inverting amplifier, but both are being summed up, right? Just due to the just due to having a common R3, right? So what happens is we can add, like, since the currents are being added up, right? So that current will give me, or will result into my output voltage, isn't it? So if you were to calculate the current, right? How do you want to read it? You want to read it as a current, or you want to read it as two individual branches of inverting amplifiers? Guys, what would you prefer for your simple understanding? Okay, let's go with the current part first, right? Okay, let's go with the current one first, right? Okay, close this. Okay, let's go with the current. So the current in this particular branch will be basically V2 divided by R2, isn't it? Since this particular branch over here, I mean this particular node over here is virtually grounded, or is going to have a nodal voltage of 0 volts, isn't it? Remember during our last tutorial, I told you that what happens is that there will be a virtual ground that will be formed, right? We don't want any contribution from the differential amplifier, right? Since it's a feedback controlled system, we want the amplifier gain to be controlled by the resistance, right? So the current in this particular branch is basically equivalent to, right? If you do your nodal analysis at this particular point over here, since this is virtually grounded, the voltage at this particular point is 0, right? So V2 minus 0 divided by R2 is the current in this particular branch, isn't it? So what happens is, okay, so what happens is the current in this particular branch is V2 divided by R2, right? Okay, V2 divided by R2. Is that fine? Right? You get this part, right? V2 divided by R2. Okay, now that is one current, right? One set of current. And then the current in this particular branch, is basically, okay, let me write it over here. So current in this particular branch is basically equal to V2 divided by R2, right? the current in this particular branch is basically equivalent to V1 divided by R1. Okay. Now we know the current in this particular branch, in this particular branch. So what happens is all the current will total up over here, isn't it? Right? Since there is no current, there won't be any current flowing into this op-amp, right? It rather will be just flowing into this total branch, right? Now, in order for that to happen, these two currents will add up, right? This will add up with this. Oh, wait, sorry. This current will add up with this, right? So basically we have whatever current we have, right? Now these two will add up in order to get my V out. V out is basically equivalent to the voltage, right? V out is basically the voltage contributed by this R3, right? Or the voltage at this particular node is being the same voltage that is being flowed across the R3 resistor, isn't it? So that means the voltage V out is basically equivalent to the total current I total over here, right? I total over here times R3, isn't it? Okay. So if I had to add this, right, these two together, that would be V2 upon R2 plus V1 upon R1, whole thing multiplied by R3. If you expand this, right, if you take this R3 and expand it into this particular branch, into this particular breaker, what happens is you will get this particular one, right? This equation over here. Aren't we going to get that? R3 multiplied by V1, R3 multiplied by V1 upon R1 plus R3 multiplied by V2 upon R2. Okay. And then this negative indicates that since it's an inverting amplifier, so the output will be inverted. Okay. All of you get that? In fact, this also indicates that the current direction we have is actually opposite, right? The current actually flowing in this particular branch has to be in this opposite direction in order for the total current at this particular node to be 0, right? Or the total voltage at this particular nodes to be 0. Okay. All of you understood that? That's how we get this particular equation. Okay. Okay, great. If you have any queries, you can just interrupt me. Please interrupt me through your microphones, like you can speak in between, right? Or there is an option to raise your hands as well. I think you can raise your hand so that I can come back and I mean, I can come back and pay attention to your queries, right? So this is what we have. Now, once we have the equation, we just directly need to substitute our values, right? So our resistor values are basically all 20 kilo ohms. So what happens is 20 kilo ohms upon 20 kilo ohms is just basically 1, right? So what we have is V1 plus 20 kilo ohms upon 20 kilo ohms. Again, it's 1. So we have V1 plus V2, right? And this negative sign is as it is. So we have 3.2 volt plus 1.8 volt. So basically, the total of these two is equal to 5 volt. And then this negative sign is also brought down. So that is going to give us our output voltage as negative 5 volt. Okay. The other way you can read is, remember, like I said, you can read it as two different inverting amplifiers being joined together, right? This one set of amplifier, and this is the other set of inverting amplifier, right? So these two inverting amplifier voltages will contribute to the total voltage at the output. So if you pay attention, if you try doing that, the inverting amplifier over here will have a gain of 1, right? So whatever voltage we have, 3.2 volt. So we have a voltage out due to this inverting amplifier as 3.2 volt, right? And then the inverting just due to these two pair of resistors, right? And input voltage of V1, our inverting amplifier will have a voltage output of 1.8 volt, right? Now, since these two inverting amplifiers are sharing a common resistor, right? Common R3 resistor. What happens is both of these will be contributing to the voltage output, right? So we add those two voltage outputs. So 3.2 plus 1.8 volt, we have a voltage output of 5 volt. but since it is an inverting amplifier, we have to invert it. So 5 volt will be inverted, giving us a voltage output as negative 5 volt. So all of you okay with it? Any other explanation you need regarding that? Okay, so let's move on to the next one, right? Question number 3. Question number 3, an analog signal in the range of 0 to 5 volt needs to be digitized with a quantization error of less than 1% of full scale, right? Here the full scale is 5 volt. Since it ranges from 0 to 5 volt, so the full scale will be 5 minus 0, that is 5 volt, right? So the range of this particular ADC is 5 volt, right? So how many bits are required, right? So how many bits are required in order for the quantization error to be less than 1%? So quantization error is basically half the least significant bit, isn't it? Or we say half the quantization value, isn't it? The quantization error is basically 0.5 times the resolution, right? Okay. So if you want a quantization error to be less than 1%, so 1% of 5 volt is basically equivalent to, that is the first thing that we need to identify. So 1% of 5 volt is basically equivalent to 50 millivolt, right? Okay. So now we know that our quantization error has to be less than 50 millivolt. Okay. So what we do is we create a table, right? We create a table, right? And then we label each particular column as resolution of that particular n number of bit ADC, right? And we label the other column as quantization error. That is basically half the resolution, okay? Half the resolution or half the LSB, right? Or least significant bit, okay? So you have to do a little bit of punching in the calculator to find your actual value. So what happens is there's 2 methods to do this. So we're just going to show you the trial and error method over here, right? So you tabulate the result and you just fill in this, fill for all n values, right? So just start randomly, right? So let's say we pick n is equal to 5, right? Our ADC has 5 bits, let's say, right? Okay, so if we start with n is equal to 5, right? So our resolution value is basically equivalent to 5 volt or Vref divided by 2 to the power of n minus 1, isn't it? That's the formula for our resolution. So basically 5 divided by, if we set our n to be 5, so it will be 5 divided by 2 to the power of 5 minus 1, okay? Which is basically going to give us 5.31. So the resolution of this is basically equivalent to 161 millivolt, okay? So our quantization value will be half this particular value. So half of this value is going to give us 80 millivolt, isn't it? So 80 millivolt is basically greater than 50 millivolt. So this does not satisfy this rule over here that we have, right? The quantization error has to be less than 1% of the full scale voltage. So less than 1%, we mean less than 50 millivolt. So our quantization value or quantization error value should be less than 50 millivolt. So what we do is, as we increase the number of bits, our resolution size will decrease, isn't it? So we increase the number of bits. If we decrease the n number of bits, what happens is our quantization or resolution increases, right? Okay, so we increase our bit. So if we increase our bit to n is equal to 6, our resolution will now be 79 millivolt. Okay, so if our resolution is 79 millivolt, so our quantization will be basically half of this value, that is going to be 38.5. Okay, so 38.5 millivolt, is it less than 50 millivolt? Sorry, it will be 39.5 millivolt, right? So it has been just rounded off. So 39.5 millivolt is less than 50 millivolt, isn't it? So now this satisfies our condition that was given in this particular case, right? The quantization error is basically less than 50 millivolt of the full scale, isn't it? Or 1% of the full scale, right? So this satisfies our condition. So basically, how many bits are required? Now, if n is equal to 6, if n is equal to 6, so the number of bits required is 6, okay? Is that fine? Guys, okay. So the other way is what you can do is actually, you just need to write 50 millivolt right on one side. You have to check if we know if 50 millivolt is our, if we are looking at 50 millivolt as our quantization error, what that means is our resolution should be somewhere close to 100 millivolt, right? Since quantization error is half the resolution, our resolution should be somewhere around 100 millivolt, right? So if our resolution is 100 millivolt, so what we just need to do is to solve for this equation, right? Vref is 5 upon 2 to the power of n. So n is what we are looking at, minus 1, and we are looking at how many millivolt of resolution? The error is 50 millivolt, so our resolution should be 100 millivolt, okay? So 100 millivolt, right? Or we just write 100 times 10 to the power of minus 3, and we solve for n, right? Once we get our n, the approximate n, we substitute that and find our resolution and quantization error, right? If that meets our requirement, that is fine. Or else we need to increase n by one value or decrease by one value. Okay, that is by a proper calculation method, right? Or the other method is to just directly do a quick tabulation method to find your n, right? So in this particular case, our n is equal to 6. That satisfies our particular condition that was given in this particular question, right? So that means our ADC has 6 bits, right? What is the minimum voltage step of the conversion? So what is the minimum voltage step of conversion? So minimum voltage step is basically our resolution. So whatever resolution we got over here, we just directly need to write it down, right? So we have selected this particular line. So it is basically 79 millivolt, right? Remember the equation over here. The equation over here, right? The equation over here has to have 2 to the power n minus 1, okay? So it will give us 79 millivolt, okay? So this equation was slightly, there was an error in this one, right? So it is basically 5 divided by 2 to the power of n minus 1, right? Or you can directly refer to this particular equation over here. We had already done our resolution calculation over here, so we can directly write 79 millivolt, okay? That's done, okay? Now moving on to the second, on the third part of the question, it says if we want to extend the range to cover from 0 till 10 volt with the same absolute quantization error, how many bits are required? So how many bits are required, right? So we want the same quantization error, right? So what happens is, like I said, now our voltage range, right? Remember, like I said, showed you that Vref, sorry, let me clearly write that particular form. Vref divided by 2 to the power of n minus 1 is going to give my voltage step, okay, or resolution, okay? So this is a triangle, right? I just couldn't draw a triangle, right? So based on this, we want the same quantization error, isn't it? We need the same quantization error. So what happens? If we need the same quantization error, we just simply do this, right? We just simply do this. We need the same quantization error. That means 50 millivolt will be our same quantization error. So if we know 50 millivolt is half the LSB or half the resolution size, so what happens is our change over here in this particular case, this particular value will be 100 millivolt. Okay. If this is 100 millivolt, what we need to do is our Vref is 10 volt. right? We substitute in place of VREF 10 volt, right? And what we do is solve for n, right? In place of VREF, we substitute 10 and solve for n. If you do that, right, you'll get an approx n value of around 6, something like that, right? Like I said, it is up to you to decide, right, whether to increase the n number of bits or not, right? So in this particular case, what happens is we basically, again, we can tabulate the method, or we can use the method that I just showed you to solve for n, right? So if we use the tabulation method, we can use n is equal to 6, and we can see that our resolution is 158 millivolt with VREF is equal to 10, right? So it is basically, if we are using n is equal to 6, so 10 divided by 2 to the power of n, so 10 divided by 2 to the power of 6 minus 1 is going to give me a resolution of 158 millivolt. So the quantization error is half of this, right, resolution. That is basically equivalent to 79 millivolt, right? In the second, I mean, like, we check our quantization error, does it satisfy 50 millivolt? No, right? It is greater than 50 millivolt. So in order to get a smaller, what do you do? In order to reduce the quantization error, we need to increase the number of bits. Okay, so we increase the number of bits. So we next is increase the number of bits by 1. So n is equal to 7. Again, calculate the resolution, right? We'll get 78 millivolt and check for the quantization error. So quantization error in this particular case is 39 millivolt, which is less than 50 millivolt. So it satisfies the condition of having 1% of full scale voltage, right? Oh, it satisfies the same quantization error in part 1 of this particular question, right? That is 50 millivolt. Okay, so that's how you get this particular solution, right? So there's two methods. You can either tabulate the result, or either you can solve for the, I mean, tabulating the result is a trial and error method, or you can just have to solve for n just by the method that I showed you, right? You know that the quantization error is 50 millivolt. So what you do is, you know that quantization error is half the resolution size. So what it will be the resolution size in that particular case? 100 millivolt, right? So you have the 100 millivolt, and then you just need to solve for the other value, right? Okay. That is fine. You need to calculate, I mean, in your lectures, that is different. As per the question, we pay attention to the question. Over here, if we need the quantization error to be less than, right? We need the quantization error to be less than this particular value. We have to ensure that this particular quantization error is being met, right? In your lecture, what did your lecturer say? He said during our lecture, said that we have to select a value like 79 millivolt, which is less than the quantization. Yes, this is what happens, right? Our resolution size, you can see over here, our resolution size is basically greater than the quantization error, isn't it? In these two particular cases, you can see always our resolution size is double the quantization error. Okay, so we have to ensure that the result that we have is double, right? Okay. Okay. Anyways, regarding this particular question, anyone has any queries? Right? Okay, if you have any specific queries, right, you can write to me, or you can drop the question in the group so that all of we can solve that together, right? But as per this particular question and whatever we had, yeah, met the condition, right? Yes. Anyone has any queries?
So for 3 part 2, could you explain how do you get 78 millivolts? I didn't get it.
Okay, wait, please just hold on. I just quickly take the attendance first, and then I'll clear your doubt, right? Okay. For part
So
2.
3 part 2.
Okay, 3
Yes,
part
so
2.
what is
Like
the
I said,
yes.
this question over here has an error, right? It should be 2 to the power of n minus 1. So basically, the n value
Yes,
that we are going to be using is the n value that we calculated in part 1. Okay. So
yes.
if we use n, that is 5 divided by 2 to the power of 6 minus 1, isn't it?
Yes, sir.
Okay. So we are going to get somewhere around to 0.079. Isn't that 79 millivolt?
Yes.
Yes. So like I said, we don't, I mean, like there was an error in this particular question. There should have been -1, and this particular value that we have is actually just slightly wrong, right? I mean, like 79
Yes,
and 78 are close, but like I said, you have already calculated
yes.
the resolution in question number 1. So you just directly use this. Okay. That is why I said,
Yes.
just use the
So
top one.
my net went, but yes, my net went bit, so I didn't hear that part. I'm sorry.
Oh, okay. No, that's fine. I mean, like it's good. Actually, everyone gets to know about it, right? Okay. That's fine.
Yeah, thank you.
Okay. Anyone has any other special queries? Oh, the other thing, when you are reading, please ensure that there is 2 ways of calculating the resolution. So that is either VREF divided by 2 to the power of n. You'll come across this, right? When you are doing your reading, right? When you are doing your revisions as well. If you search through the internet or through the textbook, there's 2 different resolution formulas that are given. That is VREF divided by 2 to the power of n, that is 1. And the other one is VREF divided by 2 to the power of n minus 1, right? You have to ensure, you have to go back and check with your lecturer. Are you going to be using VREF divided by 2 to the power of n, or are you going to be using VREF divided by 2 to the power of n minus 1? But as per what I know, it is VREF divided by 2 to the power of n minus 1, which is being used in your lecture, isn't it? This is one side of the formula, right? Okay. The other formula is this one. So which one are you guys using in your lectures? Okay. I believe you're using the second one, right? 2 to the power of n minus 1, right? So please do clarify with him again, because you don't want to confuse yourself, okay? Okay, great. So with that, I'll conclude this session, right? We have another 2 minutes left. So if you have any queries, you can quickly ask me, or else we'll end the session, right? So in part 3, the quantization error is based from the VREF, right? So then, no. See, it says we need the quantization error, right? The absolute quantization error, right? It has to be the same, right? With the same absolute quantization error. When we are dealing with absolute, right? Absolute quantization error, we are not dealing with the percentage, right? We are basically dealing with the value, right? The value we have. So for part 1, we had the 1% full scale value, which was 50 millivolt, right? So 50 millivolt is our absolute quantization error, okay? So 50 millivolt, the absolute quantization error, is what we are going to be using this in part 3 of this particular question, okay? So that is why we are using 50 millivolt to find the solution for our part 3, all right? Okay, great. So with that, we'll end the session, right? If you have any other queries, you can join me in the second one and ask me there as well, right? This session will end over here. Yes?
So I'm from 2 to 3 session. If I'm attending this, then my attendance will be taken. I have to attend that one.
Yes. No. If you have attended this, that's fine. Because both the sessions
Okay.
are back to back. So I'm taking it. So don't worry about that.
Okay, sir.
Yeah.